The upcoming demonstration will showcase a multi-layer milk tank designed to maintain a stable temperature for storing milk. The milk tank is filled with milk at a temperature of 25 degrees Celsius, where the ambient temperature is equal to 10 degrees. The tank itself is composed out of two layers, with the first layer made of stainless steel and the second layer made of an insulating material to prevent heat losses. It is crucial that the temperature of the milk does not drop below 23 degrees Celsius to ensure its quality and safety. In addition to the tank's dimensions, material properties and heat transfer coefficient have also been given. For the purpose of this demonstration, we can assume that the radiation will be neglected and that the problem is in steady state conditions. In the first question, we are asked to determine a minimum required thickness of the insulating material such that the temperature of the milk will never get below 23 degrees. In such a problem, we can derive the thickness by setting up an energy balance, but before doing so, we should understand the given situation. It is given that the milk has a higher temperature than the ambient temperature, which means that we'll have heat transfer from the milk toward the ambient. As we are dealing with a multilayer wall problem, it might be handy to sketch the given system by use of thermal resistances that are connected in series, where the first thermal resistance describes the convection layer inside the tank, the second one represents the stainless steel layer, the third one the insulating layer, and the fourth resistance describes convection outside the tank. Three temperatures in a given system are known, with Tc being the milk temperature of 25 degrees, Ti is the interface temperature between the milk and the stainless steel, which should be at least 23 degrees, and the ambient temperature, which is equal to 10 degrees. As we are dealing with multilayer wall systems with resistances being connected in series, the rate of heat transfer through each layer will be the same. So now we understand how the system functions, we can start setting up energy balances. We will take the energy balance around the interface between the milk and the stainless steel, but taking the balance at another position should work for this question as well, which is this interface in our resistance network. Through this interface, we'll have some heat entering and leaving at the same time, which we draw here in our resistance network as well. So now we can write down our energy balance, where we know the standard expression for a closed system without sources. But as we're dealing with a steady-state problem, our system will not change over time, and for this reason, everything differentiated with respect to time will cancel out. Once we have an energy balance, the next step will be writing out all elements within the balance in terms of system variables. We know the general expression for the rate of heat transfer, which is derived from Fourier's law, which states that the rate of heat transfer is equal to the temperature difference over the total thermal resistance. We can use this to find an expression for Q dot in, where the temperature difference is the difference between the milk temperature and the interface temperature, and the corresponding thermal resistance is the thermal resistance resulting from convection on the inside. Q dot out can be written in a similar way, where we take the temperature difference between the interface temperature and the ambient, and the thermal resistance is the sum of the resistances from the steel, the insulating layer, and convection from outside. We have two expressions for Q dot in and out, but our resistances are still unknown, so first we'll define the ones for convection, for which we know this general expression, where capital A stands for the surface area that is subjected to convection. For convection happening inside, we need the area of the tank inside, which is equal to that of a cylinder, which is 2 times pi times r times L. For convection outside, we should also include the thicknesses of both layers, so instead of only using the radius, we use the sum of the radius and the two thicknesses. For the first thermal resistance, we know all numbers, so we can quickly calculate its value, which is 4 times 10 to the power minus 3. The other one contains the thickness of the insulating material, delta 2, which is unknown, so we'll keep it like this for now. For the conductive resistance in pipes, we know this general expression. In some cases, we can simplify the problem, because if the thickness of the wall is much smaller than the diameter, the effect of a curved wall becomes negligible, and we can use the expression for a plain wall as well, where the area will be the surface area on the inside, which is that of a cylinder. So we can use this to find the expression for the resistance of the steel and insulating layer. For the resistance of the steel layer, we know all numbers, so we can calculate its value. Having done this, we have an expression for Q dot in and Q dot out in terms of one unknown variable, which is delta 2. So we can start plugging everything inside the energy balance and do some rewriting. So now we'll fill in the found expressions for the thermal resistances. And filling in all known numbers gives the following expression. So we see that delta 2 is unknown, and by trying different numbers for delta 2 until the left-hand side and the right-hand side of the equation are equal, one will find a value of approximately 1 centimeter for delta 2. So by understanding the problem, setting up an energy balance, defining the fluxes, and do some rewriting, we were able to find an expression for delta 2. The next question is to derive the temperature function inside the stainless steel layer. And again, we'll do this by setting up an energy balance. For this task, we need to solve the heat conduction equation, which is a differential equation that results from the energy balance of an infinitesimal element. So we'll define a coordinate system and take an infinitesimal element inside the stainless steel layer. So we know this general expression for an energy balance for a closed system without sources. First, withdraw all fluxes. Some heat will be conducted towards our element, but at the same time, heat will be lost due to conduction as well, which are shown by these two fluxes. We're still dealing with a steady state system, so everything differentiated with respect to time will cancel out, which gives us the following energy balance. Now we have our balance and we should start to define all the elements. We can describe the ingoing flux by use of Fourier's law, where the area is the area through which the flux passes, which is 2 times pi times r times L in our case. Because we're dealing with an infinitesimal element, we can approximate the outgoing flux by use of the Taylor series expansion, which is the ingoing conductive flux plus the ingoing flux differentiated with respect to r, which we multiply then by the radial width of our control volume, which we then can write out like this. Once we have an expression for both fluxes, we can just simply fill them into the balance, where eventually rewriting gives this expression. But the thermal conductivity, 2 pi, L, and dr are constants, so we can divide the left and right side of the equation by these terms, so they will cancel out, and they give us this expression. Now we have a differential equation where the temperature is differentiated twice with respect to r, so in order to be able to solve it, we should find two boundary conditions. We know the first one already, which is the given temperature of 23 degrees at the interface between the milk and the stainless steel. For now, we will assume that we also know the temperature between the stainless steel and the insulation layer, which we will call Ts. Even though it's yet still unknown, we can determine it later on by the thermal resistance network that we defined in task A. So we have two boundary conditions, and the next step will be solving the differential equation. We're going to do this by integrating, which results in this expression where C1 is just a simple integration constant. Second time integrating gives us this expression where a and b are integration constants. C1 has been rewritten to a by taking the constant outside the natural logarithm. So now we can fill in the two boundary conditions that we just found before. And if we do some rewriting, we can find the following two expressions for a and b. If we plug this in, we find the following temperature function. Ts is still unknown, and we should find its number. We're going to do this by setting up an energy balance at the interface between the milk and the stainless steel. So remember this drawing from task A. We will use the flux that passes through the convection resistance inside and the flux that passes through the resistance of the steel layer. We already drew the balance above, which is simply that Q dot in equals Q dot out. To define the fluxes, we're going to use the temperature differences and the thermal resistances again, where Q dot in is equal to the temperature difference between the milk and the interface divided by the thermal resistance of the convection inside. And Q dot out is equal to the temperature difference between Ti and Ts divided by the thermal resistance of the steel layer. We already found the values for the resistances in task 8, so we can start to do some rewriting. So first, we'll plug in the found expressions and we'll make sure that Ts becomes free. Then we can fill in the numbers and eventually we'll find that Ts is equal to 22.94 degrees. So now we know all variables and we can fill in the numbers, where ln1 is equal to 0 and cancels out. So by setting up the conduction equation from an energy balance and by solving it, we were able to find the function for the temperature profile inside the stainless steel layer. In this task, we were asked to draw the temperature profile from the center of the tank towards infinity, and the first step will be defining all interfaces that we have. Then we can sketch the maximum temperature Tz and the minimum temperature T ambient. Then we can draw the temperature at the interface, which is just below the temperature of the milk. The next temperature will be Ts, which is really close to Ti as calculated before, and this is due to the good thermal conductivity of the steel layer. Then we should also draw the temperature at the interface between the insulation layer and the environment, which we will call Te. This temperature will be far below Ts because we have a good insulation layer in between with a low thermal conductivity. The next step will be drawing all the slopes, which makes it easier for us to eventually draw the entire profile. We'll start at the center where we have a symmetry condition, and for this reason the slope should be horizontal. At infinity, the temperature will approach the ambient temperature, and for this reason we'll have a horizontal slope again. Now we have to define the slopes at the interfaces, and it is good to have a look at Fourier's law to understand why the slope changes at the interface. If we look at the interface between the milk and the stainless steel, we know that Q dot and A are the same for both sides of the interface. In practice, milk has a lower thermal conductivity than stainless steel, so from the left to the right, the thermal conductivity, lambda, will increase. From Fourier's law, we'll see that if lambda gets bigger, dTdr should get smaller, and thus the stainless steel layer should have a slope that is less steep than for the milk. So for the second interface, lambda is bigger for steel, which means that the slope of the insulation layer should be much steeper than for the steel layer. You should be able to see this yourself by using Fourier's law now. And for the third layer, the difference will be less significant as air and insulating material both have a low thermal conductivity. So now we can start drawing the temperature profile. And for the first layer, the gradient gets steeper as we're moving closer to the interface, as convection gets more significant over there. For the steel layer, we can use Fourier's law again, because if we move from the left to the right, the area through which the heat passes gets bigger, because the radius of the cylinder increases, which means that if A gets bigger, dt dr should get smaller when moving from the left to the right. The same goes for the insulating layer. And again, convection is significant at the surface, so there the slope should be the steepest. When we move to infinity, at some point the temperature will become the ambient temperature and it will remain there. So this shows that based on symmetry conditions and Fourier's law, we can already reason quite well how a temperature profile will look like.